Many of our towns are faced with traffic problems. The noise, the fumes, the waste of precious fuel.
Will you fill it up, please?
And people's time. All have a bad effect on the community and the environment. One traffic management measure which reduces urban congestion without the need for expensive reconstruction work is by coordinating traffic signals. In towns where traffic signals are reasonably close together, experiments show that a highly efficient yet simple method of control is by fixed time plans. This method coordinates the signals at adjacent junctions on a common cycle time. Every cycle, the signals are changed from red to green and back at preset times, maintaining a fixed relationship between signals. This can be shown on a time-distance diagram. Distance is represented vertically and time horizontally. The movement of traffic can be represented by a diagonal band. The slope depends on vehicle speeds. At each junction, the green period can be timed so that the traffic travels along the road without delay in a green wave. The difference in time between the start of green at successive signals is called the offset. The offsets are adjusted so that traffic is not delayed. The green band should be as wide as possible to allow for differing vehicle speeds. Now, suppose traffic is also travelling in the opposite direction. This traffic meets the centre junction during the red time and is delayed. At the lower junction, some passes straight through, but most is delayed again. These delays can be reduced by changing the offsets between the junctions. Further changes continue this improvement, but cause delays to traffic flowing in the original direction. Increasing the duration of the green times may give some improvement, but to the disadvantage of traffic on the side roads. Signal timings must be found which give a good compromise to all traffic. The green wave system has been used for many years, but the complex nature of traffic flow makes the calculations of good fixed time plans difficult, particularly for a network of roads. To perform these calculations for any type of road network, with any known average flow rates, the Transport and Road Research Laboratory has developed a method called TRANSYT. TRANSYT uses a digital computer. To carry out these calculations, the program requires certain information. The network layout must be defined, all signal control junctions are numbered, and the directions of traffic flows between them are represented by numbered links. The length of each link must be measured. At each signal, the number and order of stages must be determined. Some stages give priority to one or more vehicle movements, others to pedestrians. The red and amber safety periods must be included. The maximum rate of flow at the signal stop line is important. It depends on the number of lanes and may be measured or calculated. What is the average speed along the link, assuming that no queue exists? Counts of average hourly traffic flows are made for each period of the day. Separate fixed time plans are usually prepared for the morning peak, for general conditions during the working day, and for the evening peak. During each of these periods, the proportions of traffic turning right and turning left at each junction are also required. Of course, some turning movements may be prohibited. All this information is recorded on standard forms and then punched onto cards for feeding into the computer. These card packs define a 95-junction network for one period of the day.
Hello Claire, this is a TRANSYT pack for Glasgow. Right, okay.
To find the best fixed time plan for this network, the computer takes about 2 hours. The TRANSYT program has 2 parts. First, the traffic model, which uses the data collected from the street to calculate how much delay the signals will cause as traffic flows through a road network. Second, the signal optimizer. Delays from the model are used to produce new timings, which are passed back to the model. The traffic model is used repeatedly by the signal optimizer to search for the signal settings which give minimum delay. When the optimizer can find no further improvement, it prints out the optimum timings for each signal and the predicted delays. We will now explain how the TRANSYT traffic model calculates delay. This piece of film, using time-lapse photography, shows a section of road controlled by traffic signals working on a fixed time plan. The action is speeded up 24 times to show the flow pattern more clearly. Notice how the rate of flow varies in much the same way during each cycle of the signals. Again, on this road, the flow varies up and down during each cycle. The TRANSYT traffic model calculates the average variation in flow rate during one cycle. Traffic is represented by a histogram. The height of the columns shows the level of flow during successive intervals of time. This is how the traffic would pass a signal stop line during the time that the signal is green. However, when the signal changes to red, a queue forms. On green, the queue leaves at the maximum rate, called saturation flow. After the queue is discharged, the pattern is not altered until the next red. Now look at the traffic which departed during the green period. A proportion turns off from the main stream. The remaining traffic moves on towards the next junction and spreads out as it travels, because individual vehicles move at differing speeds. This effect is called platoon dispersion. Traffic from other arms of the junction joins the main stream to complete the pattern of flow arriving at the next stop line. The signal optimizer now positions the green period for minimum delay. This is relatively simple on one arm, but each junction has 2, 3, 4, or more opposing arms, and the positions of the green periods must be a compromise, giving the smallest combined delay over the whole network. Some large cities have traffic control computers which are capable of storing many fixed-time TRANSYT plans. A control computer has 2 main functions. Firstly, to act as an accurate timer to implement the TRANSYT plans. And secondly, to check the system for equipment faults. Once the signal plans have been fed into the computer, the start times for each plan are entered, and plan changes will then be carried out automatically at these times. Developing a system of signal coordination requires thorough testing under realistic conditions. To help with this work, the Transport and Road Research Laboratory cooperated with the city of Glasgow to install a computer system which controls 95 signals in the city centre. Conditions found in Glasgow are representative of many cities. Some of the streets are laid out in the form of a rectangular grid, while in other areas the pattern is less regular and is similar to other major towns in Britain. Some streets are heavily loaded and some lightly loaded. There are narrow streets, some of them with parked vehicles, two-way streets and also major one-way streets. There are complex junctions and junctions with pedestrian facilities. Of Glasgow's 95 centrally controlled signals, 57 have pedestrian phases. Junctions without signals also feed traffic into the controlled network. The Transport and Road Research Laboratory has tested the transit method in Glasgow using the floating car survey technique. This technique makes use of specially equipped cars which are driven throughout the working day along selected routes within the controlled area. Each of the cars carries a paper tape punch, which records speeds, distance travelled, and stopped time. It also records the time of passing selected points in the network. These journeys start at known times throughout the day and are repeated every weekday for 2 weeks to test each method being evaluated. Normally, a new method is compared with a standard control policy. Measurements showed that TRANSYT reduced average journey times during the working day by 16% compared with the original vehicle-actuated system. The greatest benefit of 23% was obtained during the evening peak, when traffic conditions are worst. Delay has been reduced by more than 30%. How do buses fare under a fixed time system, optimised for faster vehicles which do not have to stop at bus stops? The answer is that they gain considerably from the general improvement, but the number of passengers carried justifies further benefits. With increasing pressure to improve public transport, a modified form of the transit programme has been developed which finds signal timings that favour buses. Two important changes were made to achieve this. One was to model buses separately from other traffic, so that account can be taken of their lower speeds and of the time they spend at bus stops. The second point is that delays to buses can be weighted as being of greater importance than delays to other vehicles. On average, cars carry 1 to 2 persons each, and the number of occupants in these cars is equal to the average number of passengers carried on a bus. The waiting on bus delay can be chosen such that the signal optimizer minimizes passenger delay rather than vehicle delay, as in the normal transit program. In a test carried out in Glasgow, the bus transit timings produced a further reduction in bus journey times of 8% throughout the working day when compared to normal transit. Previous studies suggest that this equates with a 16% reduction in delay at signals. There was no measurable disadvantage to the rest of the traffic. Any system capable of operating transit timings can implement the bus priority timings with no extra equipment. All that is needed is extra data: bus routes, bus flows and speeds, and the average stop time at each bus stop. The annual benefits achieved by using the transit method in Glasgow are estimated to be about double the cost of installing the computer-controlled traffic signal system. Schemes using the transit principle are being installed or planned in city centres. The transit programme is freely available from the Transport and Road Research Laboratory and has been widely distributed throughout the world. It has been compared with other control methods, not only in Glasgow, but also in London and other major cities in Europe and America. To date, no method of control has been found to give a better performance.
Sound less dim swellings and straight.